Welcome everybody to our small presentation of our TUM lab, RoboLab, our clay 3D printing setup. And yeah, we're excited to have you here and to show you what we can do and what we also can't do and will do in the future. So the agenda will be as follows. First, we'll show you some of the equipment that we have that will give you an actual demonstration of the printing, 2 of those. Maybe for the ones that don't know us, maybe Martin, you want to say 2 words about yourself?
Yeah, so I'm Martin. I have been working at the chair for at the CCBE chair now at TUM since the last 5 years. And I have been working intensely on the robot setup. So that's why I'm here. I'm helping Luca with his project. I'm giving some advice on how to use the robot. And yeah, basically that's me.
Yes, so just briefly for the ones that don't know me. So I'm Luca. I've started as a PhD at the CCBE chair last year in October, and I'm responsible for work package 3 in the AM2PM project. So it's coined learning by printing. So what we try to do is we try to gather information about what we're printing and then building models that learn from those in order to optimize future prints, but also eventually at some point to optimize while we're printing to get better results, better quality, or just general performance. And we also have Sebastian Nepomuk with us here in the background. Shout out to them for helping us. And yeah, I think we can get started with Martin showing you our setup.
So the main star of today's show is not us. It is our robot setup, of course. So what we have here is a UR10E from Universal Robots, which is connected via TCP/IP connection to the controlling computer over here. And attached to the robot, we have a clay extrusion system, which is basically built by this RAM extruder containing the clay reservoir and a motor that pushes it out, which is connected to the print head, which has another motor to fine-tune the extrusion process. Both items are connected to our control box over here, which is again connected via USB to the controlling computer, and basically sets the speed of the extrusion. Aside from the extrusion setup, we also have a couple of sensors that we are using. We have underneath here the load cell platform. You can basically see directly on the display the weight like a kitchen scale, but it is a bit more powerful. We have a direct LAN connection to our time series database server, which is in the background. At the same time, we also have something that is not connected right now. So we have also our small environmental sensor, which basically detects the temperature and humidity in the room, which we can basically just put next to the system. Both sensors here will transmit the data every 0.1 seconds to our time series database. So we have a very fine resolution, and our platform here has a accuracy of 0.1 grams. So it's also quite accurate. All right, I think.
Yes, one thing to note also is that the printing platform consists of 4 separate load cells that each send the signal separately, and then we can aggregate this later in the database. So just one slide.
Each corner of the platform is basically one sensor. We will then directly dive into our first experiment. We will print a small wall section with a zigzag infill. And for that, we already prepared the FIM model. And to explain that in more detail, we have prepared some slides. So what is fabrication information modeling? I guess some of you have already heard a bit about it. To make it just brief and very lightweight, FIM is supposed to be an intermediate layer between digital design and the automated fabrication on the other side. You can see that basically in the middle part, we have set up a data structure based on the BIM exchange data format IFC. And we use that format and represent it as a graph database. So this is basically shown in the middle. For the print, we can basically extract a component from a BIM model, transform it into a component model, a component FIM model, and then use that for the printing process. If we export the FIM model, we can basically see that here. We wanted to show the slide, sorry. We can, in the FIM model, display or also show the process data. In our case, what we prepared is a small print of a wall section that is only 4 layers high. So what you can see in this slide is the task plan for it, which is very simple. It's a sequential task. It starts with a start event and then comes up with a move task, making the robot move to the initial position, which is defined by a virtual element in the IFC data format, storing the location. After that, we have 4 print tasks in sequence, which should print each layer. And each layer in the IFC data format is represented as an IFC printing layer. And this is connected to the print path. So all the geometric information is available via the task. And yeah, in our concrete example, we have like the graph structure that I showed previously. We can switch over. So this is what it looks like in a more complex manner. This data is then interpreted by our control tool. So we use Python script to just import the data and transform it into robot motion. So once I start this tool, we can specify the layer transition area, which I keep as a default. I can close this display and we can start the robot. So it takes just a bit of time to initialize the robot movement. It will then move to the starting location. This is the first task. And then there's a slight glitch, but it will start soon. And now it executes all the print tasks. This is basically it. So at the same time as it prints, we can track the weight on the platform, which is visible in our time series database. All right. So the first layer of the print is a little bit fuzzy. Let's wait 1 second. And just 1 minute. So we can display the influx data. What you can see here is the load information of all the 4 load cells over the printing time, and we can basically track it during the whole process. In the first layer, we're also going to introduce a small defect, so we can switch off the extruder anytime. For example, I will do that now. And what you should see in the graph, in the time series data, is that there is an irregularity. So it is directly visible here. And once the print is in the next layer, we can also again see the defect in the load cell data. And we can also add another defect, make it more interesting around the corner. And yeah, so again, in the time series data, you can directly see it. What you can also see is geometric information. Once the printer goes around the corner, it slows a little bit down, so it's a little bit slower. And the extruder is not as fast to react, so there is a bit of over extrusion. That's why we have this jagged curve visible in the load cells. So again, we passed the defect section, and you could directly see it in the graph as a small dip. Coming to an end. 1 second. Now we are on the second defect. You can again see a dip in the load cell. And later, once, I guess we can also finish it up now. As okay. Nothing important will happen. So now we can also see the aggregated curve. There's a huge mass display in the beginning because that's when the robot touches the platform. So this is always indicating the start of the print. And then we can see the first layer is a little bit tricky to 1 second. It's a little bit tricky to interpret because the platform is not completely level. It's not completely flat. And therefore, we have some deviations. But once we are in the second layer, everything is quite smooth, and you see a linear inclination over the whole process. And what we basically can see here is the first dip, where we first switched off the extruder, and there's a second dip over here where we switched off the second time. And we can, in between the layers, we can see that there's also a dip in the mass flow, meaning there is a small pause and it goes up, so it relieves some pressure and then continues printing. So there are clear indicators. Okay.
Maybe we can also just briefly look at the final, or let me go here. Whoops. This is how it looks like with these defects. Maybe you can see them a little bit. Yep, I'm going to clean this now.
Mm-hmm. At the same time as the load cell data, we are still refreshing, 1 second. We can also see, so this is the individual load cells. We can also check out the robot velocity, which is showcasing in which direction the robot moved. There's 3 values here. We have the in X direction, the velocity in Y direction and Z direction. And you can clearly make out the geometric shape from it in a bit. At the same time, we can also store the robot coordinates, meaning the 6 angles of the robot. And we can also track voltage. No, this is the current and the voltage of the joints. So with that, we can also calculate the electrical power consumption. Okay, that's it for the first demo. I think now Luca will go into a little bit of detail on learning by printing.
So what the goal now would be, now that we have this printing setup, we are able to collect sensor data. We want to be able to interpret that data and learn from it. And for this, I will show you a slide just to briefly explain the flow that we're imagining here. Exactly. So basically, what we're trying to achieve is we have a data set of experiments. Data set meaning we created the experiment, we conducted it, and then we captured data with it, sensor data. And then what we want to do is we want to evaluate that data automatically. So we want to have an understanding of, was that a good print or a bad print in terms of quality, performance, energy consumption, any kind of attribute you might find relevant. So there we have a machine learning evaluation model that evaluates that data and in essence labels our data set, right? So now we have experiment with input parameters, and then we have a performance associated with that that is generated by the evaluation model. The next step then is to train a prediction model, also machine learning based, that is able then to get an understanding of which parameter combinations lead to what kind of performance. And once we have the setup, we can now use that prediction model in order to calibrate the upcoming experiments, because we have an understanding of, we know the landscape between input parameters and performances. So we want to calibrate the upcoming process, the next experiment. And that's what you can see on the top right. So then we go through just executing FIM and running the experiment on the bottom right. And then we're measuring that experiment and adding it to the data set. And then the flow or the loop goes into the next iteration. So basically what we're trying to achieve here is to have an increase in performance and robustness over time. With each experiment, we should get better, or we should have a trend of getting better. And in order to validate this, we created a study that we conducted a month ago. And in this study, we wanted to evaluate basically the structural integrity of the printed object. And we looked at the connection between the inner pattern and the outer contour of the print. And we could have several situations here. So we could have no overlap between the inner pattern and the outer contour, which would probably be bad for structural integrity. And then we could have an overlap with a certain length or width. And then once we have that, we are able to give it a performance. So in this study, that's the focus, but we wanted to make it a bit more interesting and multi-objective. So first of all, we have a bunch of parameters that we use as variables in the study. So we have the print velocity, we have the height of the layers, and then we have a parameter that adjusts the print path. And then the performance that we're interested in is the strength of this connection between the pattern and the contour, the filament width that we want to have as designed, and also the processing time. So the faster, the better. So we have competing objectives here. And with this, we then can formulate an objective that is a combination of these performances. And here we said we care about the node connection the most, so we weighted it by 3. We also care about the filament width, and we somewhat care about the processing time, which is 1.5. And that's basically our performance of the whole system, or in more classical terms, just our objective. So that's the basic setup of the study. And now just quickly going through the process again. So the first part, we want to build up a data set. So we're just conducting a grid search, or we're just creating different experiments across a grid of variables. And that will give us, in our case, 27 different experiments that we conducted in order to generate an initial data set. Then the next step is to evaluate those experiments by our system performance. So each experiment has a label now, the system performance. And then we want to now run this loop in order to improve our performance with new experiments. So we're conducting new experiments, they're being placed somewhere, and then we converge towards an optimum. So that was the hypothesis, and that's what we tried to test. Okay, so I can now show you how this looked like. So we have a study management tool, which is called Airtable. So this is where we document all our experiments, and also FIM pulls the parameters directly from Airtable. So this is completely integrated in the process. And you can see here that we conducted 42 total experiments. 27 of them were data set experiments, and 15 we ran through this loop. And here we can see for each experiment, we have assistant performance and some more information. And here we see the variables that we set. So for these first ones, these were defined statically by us. And then eventually, when we go more down, we enter the calibrated experiments, where now the numbers get a bit more, what's the word, a bit more complex, not really complex, but not as statically set. And we also can see how well we predicted that performance. And we can also look at this in graph representation. So here we see how the performance went through the data set experiments. And down here, we can see for the calibrated experiments. And note that the scale is different. So here is 40% to 90, and here we have 75 to 90. So you can see we have an increase in performance over time, and we reached at max 88% performance in that study. And here we can also see how well our model predicted for those calibrated experiments. So you can see the prediction is quite good most of the time. And what we'd like to do now is we'd like to extend the study that we already did by an initial additional experiment. So experiment 42, which has not been conducted yet. So it's ready to be executed, and that's what we're going to do now.
Right. I again prepared the FIM model. So we have the same graph structure available. We are now printing 4 layers instead of 3, so it looks a little bit more complex. And what we are going to do to measure the nodes or to predict, to see what the performance is, we're using the attached camera that is on the robot head. And we are taking pictures of the individual nodes. And to do that, we have to insert additional tasks, which we are doing with an auxiliary script. We're now
slides. We can quickly show it in the slides in a more simplified form.
Mm-hmm.
So if you, exactly. So here we have our process from before. And what we do now is we just insert additional sense tasks. So after each layer that we print, we also want to take an image of all of the nodes of that layer. So you can see just in the FIM graph representation, we added additional tasks, and this will then be executed by the robot.
Right. If we go back to the control PC, instead of this graph, we then have a more complex graph. And each sense task, which is depicted here, is a series of taking pictures and movements. So once we have done that, we can set the Airtable synchronization, or we can enable it. We only have to specify the experiment code so that the program can pull all the necessary parameters. And then we can run the experiment. I will just hit run again. Then it will show us the initial layer. We can then select the transition area and then start the whole process. So there is a small glitch, 1 second. It started sending without the robot. So as a safeguard in Airtable, the experiment, once it's executed or once we start the execution, there's a flag setting it to running. So we cannot just redo an experiment. We have to manually control it in Airtable. And now Luca has done that, so we can restart the experiment. And it should say everything is fabrication ready in a second. There we go. Green checks. Then we can again select the correct port and then start the process. Should start any second now. There we go. This time with movement. And now we have our experiment.
So what we can see here now is that the speed that the robot is executing this, as well as the layer height, have been completely defined by the prediction model in order to optimize the performance based on our objective. So as you can see, it kind of went for a rather slow speed. And even though faster speeds are better in terms of the objective, apparently the slow speed gives better quality, which in the end outweighs in our objective the speed. So that's why the model chose here to go for a bit of a slower execution than last time. And now we're taking the pictures. Picture 1, picture 2, picture 3 of the first layer, and we continue. So that was this sense task that we added to the execution. And these images have now been directly sent to our FTP server. And we can use them for evaluation later in also an automated process.
Yeah, this will run for 3 layers.
4 layers, I think.
4 layers, right?
Yeah.
And each layer is completed in a time of about 40 seconds.
A bit longer, I think.
45.
46, 45, something like that.
So it takes a bit of time, like 3 minutes.
So now we're finishing the second layer, and we're again taking images of the nodes of this internal pattern versus contour, and continue.
For the evaluation, we have to note that the first layer is usually a little bit different because it deviates a little bit because of the uneven ground. So we don't, we disregard the first layer in the evaluation model. So the second layer was actually the first set of pictures that we are actually taking into account.
And the filament width is also directly depicted from the images that we take. So these images serve 2 purposes. 1, we get the overlap, and 2, we get the width of the filament. Okay, now we're going to our last layer.
All right. Almost there.
Okay, and the last set of camera tasks is coming up.
And that's it.
Yes, that's the end of the process. Okay, so what happened now is we have all of the images that have been sent to the FTP server. We have all of the parameters documented in Airtable. And the next step now is to basically, we want to now use, 1 second. There we go. So we now want to evaluate, and for this we run a Python script again. And this is also directly connected with Airtable. So what I can do here is, again, I select the experiment code. I quickly need to also connect to the server so that we can pull the images. There we go. And now we're going to run this. And you can see how the different edges look like, or the nodes look like. So the camera is not the best. We definitely want to upgrade. And now we're automatically computing this overlap, as you can see here. So I can just click through all of the nodes. Yes, that's it. And now we're running the evaluation and updating the performance in Airtable. So what we can see now in Airtable directly is we have here, we have a new system performance for the 40-second experiment of 83.2. And our prediction model predicted with an accuracy of 95%. Okay, so here we can see we have a slight dip in performance to the previous one, because it's not always deterministic, right? Things can happen. And even if the overlap changes just a little bit, this can impact performance. And we can now look a bit more in detail in the separate performance attributes. So here we can see the filament width performance, the node overlap performance, and the process duration. And from the last experiment, the node overlap went down, filament width as well. So the prediction model regressed a little bit.
Mm-hmm. Maybe to showcase a little bit what the performance means, we can go into a little bit of detail here. So the speed performance is clear. We want to be as fast as possible. But we also want to make sure that the node connectivity is well defined. So we have set it to a certain value, like the width of the connection should be moderately thick. If it's too wide, it's not good. And if it's too small, it's not good. So if it doesn't intersect too much, it's too small. If it intersects too much, it is too wide. There's too much material displacement here. I mean, this can be set anyway, but this is how we defined it for this experiment. And yeah, and the overall quality of the filament width is also important. It should be 6 millimeters.
Yep.
All right.
Okay. Now that we've evaluated our experiment, in order to complete our fabrication learning loop, we now want to adapt our prediction model based on this new information that it has and create a new experiment with the optimal parameters based on the information that it has. So I'm going to show you some code again. So now we're running the prediction model code, where we set the new experiment name, and we're basically just pulling now the data set from Airtable. So we're running the prediction model, we're loading the data set, and now we already trained. It's a very simple model, right? We have 3 input variables and 3 performances. So this is a visualization of the prediction model, where we just look at it from different perspectives. So here we have the layer time and the path offset as a variable, and the node overlap performance plotted on the y-axis. And this shows us where the optimal regions are in terms of node overlap performance for those variables. So we can see this diagonal here that gives us optimal node overlap. And we can do this from a bunch of different perspectives. I'm just clicking through here. This is also quite an interesting one. Okay. And now we predicted new optimal parameters. We created a new experiment in Airtable. And as soon as that is done, we set these new variables. So now we can see in Airtable, if we go back to this overview, that we should have a new experiment here with these variables. And this is the new optimal prediction by the prediction model. And what we could do now is we can just say, okay, we execute this experiment now, and then we add 1 iteration to our learning by printing loop. So that's basically what we did in the study 15 times, and that was the 16th one.
Mm-hmm.
Yes. So
that's it, I think, yeah.
That's it from the demonstration part. So yeah, one important thing to note is that this study was just a proof of concept, right? We didn't optimize for what are the most relevant attributes. We just optimize for, we want to have multi-objective, we want to have this loop, and we want to make it as easy as possible for us. So small structures. And in the future, what would be now really interesting is to figure out, okay, what sensors give us the most important information, and how can we optimize on those, and how can we integrate them into our system. So that's what's upcoming, and where all of you, we need your expertise as well. And on top of that, we also want to look into how can we do this adjustment on the fly rival printing, right? So now we did this whole loop offline. We took the images, we evaluated them offline, but we already took the images while we're printing. So there's nothing stopping us from evaluating them while we're printing and adjusting the speed on the fly. So these are like the upcoming things we want to look into. And I think with this, we can open up the discussion.
Maybe I can also quickly answer the question.
Oh yeah, I didn't see it.
So if we, this camera, if we check out the print path, if we go faster with this printer, what will happen is that around the corner, the robot will kind of drag the material with it. And if we kind of move along the zigzag, the zag will move inwards. So it will open up a cleavage between the outer parameter and the zag. And that's very unfavorable and is kind of decreasing the stability of the overall component. And we want to control that with the help of machine learning.